Hi, I'm Dan, Mike Zero Whiskey Uniform Tango, and welcome to my YouTube channel. So, over the last couple of weeks, the UK had a record heat wave, and here in Cambridge hit temperatures of 40 degrees. And unfortunately, during this thermal stress happened to cause my Spectrum Analyser, an Agilent E4407B, so a 26 gig Spectrum Analyser, to start issuing error messages every time it was booted. So let's have a look at it and see if we can fix it. Okay, so here we have the front panel of our instrument, and we can see that this instrument has two faults. This system alignments all is just a thing that's needed on startup, which I haven't done because there's no point while the internals aren't working, so we don't need to worry about that. The other two faults are that the clock and date and time is rubbish. The device has an internal battery backed up crystal and clock that I've never been upset about enough to warrant taking the instrument apart just for that. You know, these are relatively expensive bits of kit and fairly old. So the fact that the date was a bit wrong did not warrant breaking all the seals and potentially risking damage it. However, the concerning one is this new one, this LO unlevel. So this means that the local oscillator inside, it has a circuit that tries to set it to the correct level to ensure the mixers work optimally for all frequencies, and either the local oscillator is failing to output the right power, or the leveling circuitry is failing to control it accurately enough. Now, one important thing that I should mention is there are two LO warnings. There is LO unlock and LO unlevel. So unlock is it's unable to achieve the right frequency, unlevel is it's unable to achieve the right power. And of course an LO unlock would be much more serious. So this implies that the LO is actually outputting something at the right frequency, but the fact that it's unleveled suggests that we're just not getting the right amount of power for the ALC circuits to all be happy. Now, one of the first things we probably should do is, there's no front end in the world that will take 9 kHz to 26.5 gig all in one go. That's just not possible. So often these instruments internally have multiple bands that they carve the full frequency range up into and switch in and out different bits of circuit as they go through these and then stitch the results together to present your results. So if we can show that this problem exists only in one band or only in certain bands, then we can start to narrow down and get an idea where that might be. For example, you can see here this is the lowest band of the instrument that goes up to about 3 gig, and then you get a step in the noise floor as we swap over to another band, and possibly also another change there. So at the moment we're sweeping the full 26.5 gigahertz, but if we drop the span down to 10 megahertz, so we're now looking at a center frequency of 13.25 gig plus minus 5 megahertz, and you can see that this LO unlevel warning is gone. So this suggests that it doesn't apply everywhere, so I think the first step is for me to sit down, sweep through the entire frequency range of instruments and make a note of all the bands where the LO is unleveled, and that might give us some clues when we look at the block diagram as to where we need to focus our attention on. So here's something I noticed that was quite interesting while I was playing around, is that at certain frequencies when we're right on the edge you can get this LO unleveled sort of blink. So that implies that the LO is delivering most of what we want, but just not quite enough power. So that's possibly a little concerning, in that it suggests that something is only slightly broken rather than completely broken. So this might be a little bit more fun to debug.
Okay, so I've been over the frequency range of this Spectrum Analyser and written down all the bands where I have a problem. So the first thing we should do when presented with this, we have sort of a load of numbers, is to try and work out how they're related and see if we can find anything common. However, nothing is immediately obvious. You know, one of the most common things to look for is, are they harmonics of each other? You know, exact multiples, so 2 times, 3 times. However, these are quite a long way off. You know, the second harmonic of 2995 is a long way away from the sort of 6.7 gig we have here, and likewise with this. So I think there's something a little bit more complicated going on. So the next step is to open the service manual, which has block diagrams of how this instrument works, and see if we can find the relationship between these bands. Okay, so here we have the block diagram. It's quite a beast. This is just the RF section, and if you want to see a full explanation on how everything works, again, I'll recommend the excellent video by the Signal Path. I'm just going to go through the things that are directly related to my problem and see if we can get any clues as to why these frequency bands are not working. So, our signal comes in over here. I don't have this input attenuator, so it just goes straight through and along to this switch. And this switch will put the signal one of two ways. If we're looking at signals below 3 GHz, it will go up and this way. And if we're looking at signals greater than 3 GHz, it will switch the signal down here. So looking at the less than 3 GHz path first, what we do, we go through a low pass filter to reject any signal content above 3.1 GHz through a DC block, bit of protection. This here is an amplifier that can be switched in if you want more gain in the front end. I don't have this. And what we have here is the first mixer. And this converts our signal to 3.9214 GHz. So we have a tunable LO in here that will convert anything from 9 kHz up to about 3 GHz and convert it to 3.9214 GHz. Then we have a bandpass filter, a bit of gain adjustment, amplifier, a notch filter for 5.5 GHz. I'm not sure exactly why that's needed. It might be some harmonic of the LO or some artifact of the mixer, but we'll not worry about it for now. And then it comes into this second converter. And what we have is a bandpass filter to remove any sort of spurious content that's been added by this amplifier or this mixing process. And then we have this second mixer, which has this 3.6 GHz LO. So the frequency we're going to get out of here is 3.9214 minus 3.6, which is 321.4 MHz. Now going back to the other path, so back to our switch. If we're looking at signals greater than 3 GHz, it goes through here. Here we have a tunable bandpass filter, and it then goes into this harmonic mixer. And what this allows us to do is we don't just have to mix with the fundamental of the local oscillator, we can mix with its second harmonic, its third harmonic, its fourth harmonic, etc. And what this allows us to do is for a smaller tuning range in the local oscillator, we can have a wider frequency coverage. It does mean it's more complicated, but it prevents needing an oscillator that's tunable between 3 and 26 gig. Again, a very quick explanation, and check out the signal path if you would like more details. Signal then goes down here, through this switch, which is always set to this position, through a bit of gain, along here. And what the LO here is chosen such that the signal on this chain is also 321.4 MHz. So this then goes along here, up here, into this. We have a bit of bandpass filtering, and this switch either can select from this path or this path, but the signal by this point has all been converted to 321.4 MHz, and this is our first IF. You could argue there has been an IF frequency of 3.9 GHz here, but that's not true for all stages. So our signal then comes down here, and what we have in here, into here, are 300 MHz. We then have some bit of filtering, and this mixer takes our signal down to 21.4 MHz. So the LO here is fixed at 300 MHz, through here, through a filter, and out to the IF board. So to help us keep track of what's going on, the block diagram has this helpful table in the bottom, and this tells us how the RF frequency that we're looking at relates to all the LO settings, what band we're using, and what path it's going. So this band 0, so this is our sub 3 GHz path. Sub 3 GHz path. So this is our path if we along this top here. And the fact that we see issues when the RF frequency is above 3 GHz implies that the stuff that's exclusively in this path is probably fine, because we're looking for something that's common to more of these bands than just that one. These four at the bottom, these all use our harmonic mixer. And what they allow us to do is to convert from the RF frequency that our input is at to what the local oscillator is. So the way we do this conversion is we take our frequency, so say for example this 6.78 GHz, we know our IF is 321.4 MHz, so that means that we need an LO of the sum of these, so 6780 in megahertz plus 321.4 gives us that we need a local oscillator frequency of 7101.4 MHz. And the fact that this is a 1 tells us that this number is the fundamental, so the first harmonic of our local oscillator, and we can see this corresponds to what the LO is running at. If we take a more interesting example, let's take this one here. So if we want 19.2 GHz of RF, so 19200, our IF is at 321.4 MHz, so let's add that on. and this tells us that we're using the fourth harmonic of the LO, so the fundamental of the LO will be a quarter of this, so dividing that by 4 tells us that our LO is running at 4.88 gigahertz. Okay, so what I've done is, for each of the bands of interest, I've gone into the block diagram and tried to work out what the LO frequency is. And now we've got a really clear picture of what might be going wrong. You can see that the LO, where all this problem starts, are pretty much exactly 6.24 gigahertz, and they agree with each other very closely. So if we look at the instrument has 5 bands. In this band here, we don't actually get the LO up to 6.2 gigahertz, so we can ignore that. And other than that, these perfectly mapped to, for these 4 bands here, the LO being 6.24 gigahertz up to close to the top, but not quite. So you can see here the LO runs up to 7.02 gigahertz in this band, but we only have issues up to 6.9. So I think it's time to take the instrument apart and see what we can find in there.
Okay, so I think the first thing to do is to take these handles off. They just have an Allen key in each side, so let's see how this goes. Okay, so next we have these 4 Torx head bits that are holding on this back cover, so we'll undo those and then be able to slide that off. Okay, so having watched the signal path video, I happen to know the RF deck is underneath this massive plate on the bottom, so I think the next job is to undo all of these screws and try and get access. Right, so the instrument's now running with the side off, and we can see some of the diagnostic LEDs coming on. This top one here is telling us that the local oscillator is unleveled. We'd expect that to be on and off, given that that's the error we're trying to fix. These 2 down here are telling us that the PLL is having a hard time locking. But given that we get no unlock warnings and I can't actually find a frequency where they're statically on, I'm going to assume it's just an artifact of the unlevel indicator, and hopefully if we fix this, these will go away. Now the first rule of troubleshooting is to always check your supply rails. I'm expecting these to generally be fine. The reason is they supply so many components on this board that if any of the major rails were wrong, we'd expect to see far more errors or far more serious ones than this LO specific one we've got. And luckily the nice folks at Agilent hopefully label them all at the top of the board here. So let's measure them all and see what we get. So, minus 15 volts, looks good. Plus 5 volts analog, little bit low but looks good. Plus 15 volts, looks good. Plus 5 volts digital. That's jumping around a little bit more than I'd like, but generally looks in the right ballpark. Minus 5 volts. Looks good. And plus 28 volts. All good. Okay, so I think we need to do a bit more digging specifically in the LO bit of the circuit and see what we can find wrong there.
Okay, so we're back to our old friend the block diagram, and what I've done is I've zoomed in on the section specific to the local oscillator and its power levels. So what we have here is our YIG oscillator. YIG is just the chemicals it's made of. It's basically a voltage controlled oscillator, and the use of this weird chemical allows us to get a very wide tuning range. These 2 signals coming in are the voltages used to set the frequency, and actually we don't care about this. All this circuitry here is involved in setting of the frequency, and given that we get no PLL unlock warnings, we're going to assume that the frequency is correct. We then have this thing that they call a modulator. What this is a voltage controllable attenuator, so it's a bunch of pin diodes where you can control the loss through them based on what voltage you apply. We then have a fixed 6 dB attenuator, an amplifier, and 3 directional couplers. Now this first one is used for setting the power. So what we do, we go here, we go through a power detector, and compare this to the requested power, and this is used to sort of tune this modulator or attenuator to set the power level correctly. We then have a second one, and this one is used to tap off some of the power in some sort of frequency control circuitry. Again, we're going to assume that works. And we have this one which taps off some of the aux LO circuit. And then it goes up here into our first mixer. Now, this J5 here is an SMA connector, and if I had a second spectrum analyzer, it would be really easy to check on that port, am I getting 0 dBm across all frequencies? However, I don't have a spectrum analyzer and I don't have one easily available to me. So what I'm going to try instead is we're going to have a look inside this sort of power detection circuit. And the voltage here will be a DC level proportional to the power. So if we measure there, we can see what power it thinks the LO is putting out. And if we measure it here, we can see the drive signal it's applying to this modulator. So if we see that this is sort of trying to set the LO to minimum attenuation and still not getting enough power, then we can be fairly confident we're getting low power output through this chain. Now if the YIG is broken, I'm a little bit screwed. I've had a look, there is one on eBay for about £1,200, but that's more than the cost of some of the cheap Rigol spectrum analyzers and most of the cost of a replacement, so I'd rather not do that. So hopefully it's either this pin diode or this amplifier. But first let's have a look here and see if we can get any clues as to what's going on. Okay, so let's walk through the schematic and how it's implemented on the PCB, because once we start showing oscilloscope traces and what's going on, it's a bit difficult to show you that on the board at the same time. So here we have our YIG oscillator. So this is our YIG here. So this is outputting our sort of 4 to roughly 7 gigahertz, and the first thing it goes to is into this modulator, and the schematic's up here. So here we have this 0 dB pad, and then here we have our 4 pin diodes with the butterfly stubs, that's all down here. Then here is our sort of DC modulation drive signal, so this is what comes in up here, and that is controlling the loss through this attenuator. And then we have our 3 dB pad out here, before we go on to the next stage, which is the amplifier. So here's the amplifier, and what we can see is we have 1 gain stage, 2 gain stages, these are here and here respectively. We then have a Wilkinson power splitter, it's here. Note that this is not doing any sort of push-pull topology, this is just sort of power splitting and combining to get more power out of sort of smaller amplifiers. We then, for each of these, we have 2 stages of gain. So these correspond to here and here, and then we combine them back together again to get our output. This then goes into our directional couplers. Now I can't actually see the directional couplers from this side, but this circuit here, this node here is this node here. So here we have our power detector, and we get a DC voltage out here, which corresponds to this arrow drawn in blue. So that's our DC voltage corresponding to our power level. And then this goes out of here into these op amps, which are used to, and then this LED is what's telling us our LO is unleveled. So I'm going to start probing around this node here into this power detector and see what's going on. Okay, so I've captured the 4 main signals that are involved in LO power control to see if we can work out what's going on. This first signal here, so this is sweep active, so it's high while the sweep is running and then goes low as it sort of jumps back and starts again. So we've got about 1 full sweep on the screen. This second signal is the drive for that LO unleveled LED. So what I've asked the sweep to do is to sweep between 2 and 2.6 gigahertz, and we know the unlock issue starts around 2.4 gigahertz. So this is leveled for the first half where the signal is high, and then goes unleveled for the end bit where it's low. This third signal is that MOD drive signal, so the drive voltage to that pin diode attenuator. So this is a negative voltage, and it gets more negative, will reduce the loss through that attenuator. This last signal is the LOVDET, so the output from that power detector. And what we can see happening up to sort of this point here is that LOVDET is staying constant. So this means the AGC loop is working and is able to keep the output of the LO at the right power. But it's only doing this by making mod drive more and more negative, i.e. making that attenuator less and less lossy. And at this point here, that mod drive signal is about -5 volts, which is the negative voltage in the system, so we can't actually drive it any more negative. So that's the point that we run out of steam and we can't make that any less lossy, so what happens is our output power starts to drop. So this is symptomatic of something in that LO path having a gain that rolls off with frequency. Up to this point we're able to compensate for it with that attenuator, but after that we just can't do any better and we see that roll off. Given that the LO is staying constant all the way up to here, so from here all the way up to here it's managing to keep it steady. That looks like the pin diode modulator and the associated feedback loop with that is all working properly, because it is able to stabilize that. So I think we need to have a look at the amplifier. Here is our amplifier, and what we can see is we've got sort of 6 very similar stages. Here we go with this sort of Wilkinson splitter and this 2 stages and recombined. So let's look at one stage in particular and see if we can work out how they're all working, and then they'll all be pretty similar. So what we've got here is our drain supplies coming in up here at the top. We've then got a bit of filtering, bit of RF blocking, bit of decoupling, and our gate supply is coming in here. So if we scroll down to how the biasing circuit for this works, so here we have the biasing for that stage, and what we had was our transistor was connected across here. So let's try and analyse how the circuit works and see if we can make sense of it. So here we have this VCF RF, and on mine this measures 4.81 volts, which seems a little bit strange given how precise the resistor value is used. I mean, here they've used like a 619 ohm rather than 620, which is a more standard value. So given they're controlling the resistances that tightly, I'd have expected the 5 volt rail to be more tightly controlled, but whatever. It is also worth noting that on mine I have different values of resistors and actually different transistors on mine, so this is representative, but I couldn't find a schematic for my exact model number. So what we have here is these 2 resistors set the voltage on this reference, and we can work that out using our standard potential divider formula. So the voltage on there, let's assume it's 5 nominal, so it's 5 times 2150 divided by 2150 plus 619, and that gives us 3.88 volts on that pin there. And what this op amp will try and do is it will try and adjust the gate current such that the voltage on these 2 pins are the same. So assuming that it's able to be stable, we'll also have 3.88 volts here. Now we've got 3.88 volts on this node and we've got 5 volts on this node. That means we've got a difference of 1.12 volts dropped across this parallel combination of resistors. 68.1 and 51.1, so 68.1 times 51.1 divided by 68.1 plus 51.1, so the standard product over sum for parallel resistors. So that tells us we've got an effective resistance across here of 29 ohms, and if we take our 1.12 volts and divide it by 29 ohms, we get a drain current of about 38 milliamps. So that is our quiescent current into our drain. And it works the same for all of these. They have slightly different resistor values. And what the filtering means is that the RF signal is actually fairly small, so we shouldn't see any significant perturbation due to the RF. So this will all be at steady state DC conditions. So you can see here that this has slightly different values, presumably for the different transistors and the different bias levels. Someone far cleverer than me has worked out what all those should be, so I won't question it. So what I can now do is I'm now going to go through and look at all the gain and drain voltages of each, check that they're stable, and for sort of identical pairs, so we'd expect in this system that, say for example, the drain point here and the drain here, we'd expect to be at the same voltage, same for the gates, and this pair we'd expect to be the same as well. These two might be different, so I'll go measure all of those and see if we can get any clues as to if any of the transistors are misbehaving. Right, so I've been through and measured all those voltages and plotted the results here. So what we have, this set point is the voltage that the resistors were trying to set the drain voltage to. And what we can see is 4 of these devices have the same set point and 2 of them are special. And the 2 ones that are different are these 2 on the end, which makes sense. In my Spectrum Analyser, at least 1, 2, 3 and 5 are the same transistor, and 4 and 6 are a different one, presumably intended for higher power. So it makes sense they have a different set point. And what we can see is generally things look pretty consistent. However, the concern is this device here. So this has a drain voltage way lower than its set point, which suggests that it's conducting more than we're trying to get it to. And you can see the level control circuit has turned the gate voltage way down to try and restrict the current. This minus 2 volts here is equivalent to that op amp hitting its negative supply rail, so it can't turn it off any harder, and it's still unable to limit the current enough. So this suggests the device is conducting more than it should, and that's probably indicative of a damaged part. So I think we need to replace device number 5 and see if we can fix this. As a point of habit, it's probably a good point to replace device number 3 as well. And the reason for this is because this circuit expects these two arms to be the same, so the path up here and the path down here to be as similar as possible. So it makes sense to replace device 3 as well. That way we don't have one arm with a brand new transistor and one arm with a sort of 20-year-old transistor, to try and keep them as matched as possible. Now, I actually really struggled finding a part number for this. My schematic is clearly wrong, but I asked out and the good folks on Twitter actually came through, and I had 2 people suggest a part number, which I've been unable to find, so thank you, Internet. So I've got 2 of these transistors, so let's replace these 2 devices and see what happens.
Okay, well the plot has thickened. We're now getting no LO and level warnings, but I'm not liking all this spikiness. I'm just wondering if that's because I had to pry it apart and sort of all the shielded cavities aren't pressed in well, if it's not behaving. So I'm going to try bolting it back up together and see if that sort of eliminates these spikes. I've just put the top on, just done up a few of the screws, and we can see all the spurs are gone, no LO and level locked. Excellent.
Okay, while I was bolting it up, I did replace the battery. There's nothing super exciting. You just follow the instructions to take it apart, as they're all printed on there. And amazingly, you only need one size of screwdriver to take everything apart. So that's a nice touch there. So yeah, follow these instructions and you can take the digital card out, which looks like this. And the backup battery is this ST component here. And quite interestingly, actually, the battery plugs in the top of a really strange IC that I'd never seen. So here it is with it removed. And these 4 pins are where this battery plugs in. So yeah, I've never seen anything like that before, but thought that was interesting and worth sharing. But in terms of the disassembly and reassembly, there wasn't really anything to note, so I just sort of skipped through it.
Well, I think we can call this a complete success. It's all back together, showing no warnings. And don't worry about this 2.6 dB, this is just loss in the cable and attenuators. You can see if I drop the frequency down to 10 meg, and on both of them you can see that it's reading basically exactly 0 dBm, so everything's good there. And the backup battery's done its job too, and we're now showing the correct time and date, and it does save it over a power cycle. So I think for £5 of transistors, that's been a very successful pair, and it's great to see the Spectrum Analyser working again. So now I can use it to assist in the bring up of my 70 sems transverter, and I hope you'll join me for the next video, which will be looking at that. I'm not a professional video person, I'm just an RF engineer who pointed a camera at something I thought might be interesting. So if you have any feedback, it's appreciated, either in the comments or on Twitter at M0WUT. And thanks very much for watching. 7-3 from Dan, Mike 0, Whiskey Uniform Tango.